Now, moles and combustion analysis. Combustion analysis is a very specific type of question that usually comes. It used to come in O levels as well, sometimes, very few. But in A levels, it's frequently coming in A levels. What combustion analysis is that it's the analysis of a hydrocarbon. Most of the time, it's the analysis of a hydrocarbon molecule, and you try to figure out the formula of the hydrocarbon molecule by burning it. One example is, let's say you have an ethane molecule, and what you're going to do is you're going to burn it, and you're going to figure out uh, a certain amount of carbon dioxide, and let's say there's complete combustion happening, so there's going to be carbon dioxide and water that's going to be produced. Uh, and according to the ballast equation, there would be two carbon dioxides and there would be three water molecules and four oxygens plus three oxygens. That's a total of seven oxygens. So over here, there would be 7 by 2 oxygens. This is a gas. This is a gas. This is a gas, and this one is over here is a liquid. Now, um, based on the way the equation is balanced, um, you can come up or figure out the formula of the hydrocarbon. Because every hydrocarbon is going to result in the production of a different amount of carbon dioxide and a different amount of water molecules. Okay, so based on the ratio of the number of carbon dioxide that are produced and the number of water molecules that are produced, you can figure out the formula of the hydrocarbon. Now, for that, one thing that you do is you're going to assume that you don't know what the formula of the hydrocarbon is, because that's what you're going to try and find in this question. So one way to figure that out is that you make a general equation of a hydrocarbon. Now all hydrocarbons are composed of carbon and hydrogen. So what you're going to do is you're going to try and balance or come up with a general equation where the hydrocarbon is represented by Cx and Hy, where obviously X is the number of carbon atoms, so it could be anything, and Y is the number of hydrogens. Now, what we're going to do is we're going to try and come up with an equation, a balanced equation, but the equation would be balanced in terms of X and Y. So carbon dioxide and water molecules, whenever a hydrocarbon burns, carbon dioxide and water molecules are going to be produced. Now, the way I'm going to try and balance this, I'm going to look at the equation that I just made above. This was a random hydrocarbon that I chose, and I decided to balance it. Now, if you look over here, and we're going to follow that, if there are two carbons, then the amount of carbon dioxide is also two. So if you have X carbons, the amount of carbon dioxide over here would be, if I try to balance it in terms of X, it's going to come out to be X. So no matter what the hydrocarbon is, let's also make another equation of another hydrocarbon, and we can compare it with that one as well. Let's say there's another hydrocarbon and it's C7 and H16. If I try to balance it, it's going to be 7 CO2s and there would be 8 water molecules. And the amount of oxygens would be 7 into 2, 14. 14 plus 8 is 22. This would be 11 oxygens over here. Now I have these two equations, two completely random hydrocarbons, and I'm going to come up with an equation with it, where it's going to be balanced in terms of X and Y. So whatever the number of carbon over here is, the number of carbon dioxide molecules over here are exactly the same. So if it's X, it's going to be X over here. I said, what about water over here? If there are 6 hydrogens, the amount of water would be 3. That is half of the value that's over here. If there are 16 hydrogens, the amount of water over here would be 8. So whatever the number over here is, this number over here is half of that. So if you have Y hydrogens, the amount of water molecule over here would be Y by 2. Is this clear so far? Now we've balanced in terms of X the amount of carbon dioxide and amount of water. The only thing that needs to be balanced now is the amount of water molecules over here. Now this is a tricky part. So for this, we have to count the number of oxygen on the right side. So let's pick the first one. How many oxygens do you have? It's going to be 2 multiplied by 2. So whatever the number over here is, it's going to be double that. So over here there are 14 oxygens, over here there are 4 oxygens. So over here they're going to be 2x oxygens. So on the right side I have 2x oxygens over here. And how many oxygens do I have over here? In 3 water molecules, it's going to be 3 oxygens. If I have 8 water molecules, it's going to be 8 oxygens. If I have Y by 2 oxygens, Y by 2 water molecules, I'm going to have Y by 2 oxygens. So over here, I have Y by 2 oxygens. So the total number of oxygens that I have on the right side, if I add them up, I mean, over here it's 2 into 2 plus 3 oxygens over here, 7 into 2 plus 8 oxygens over here. So it's going to be 2x plus y by 2 oxygens over here. So the total number of oxygens on the right side is 2x plus y by 2. If I put them together, that's the total number of oxygens that I have on my right side if I try to balance it in terms of x and y, right? Is this part clear? Yes or no? Let's look at this first equation again. How many oxygens did I have? I had 4 oxygens over here and 3 oxygens over here. So I had a total of, on the right side, I had a total number of oxygens of 7. I had 7 oxygens. So what did I do on the left side to balance it? I multiplied O2 by 7 by 2. So to get 7 oxygens. Look at the second equation. How many oxygens did I have? I had 7 into 2, 14. 14 plus 8 is 22. So on the right side in this, I had 22 oxygens. So what did I do over here? I multiplied this by 11. So the number that I'm going to put over here is going to be half the number of oxygens over here. So if I have 2x plus y by 2 oxygens on the right side, the amount of oxygens to balance this number over here should be half of that. So you divide this number by half. It's going to come out to be x if I divide by x by half, and this would become y by 4. So the number that I'm going to get over here in terms of x and y is going to be x plus y by 4. It's going to be x plus y by 4. And now this equation is completely balanced in terms of x and y. This entire equation is balanced in terms of x and y. So hopefully this part is. Now using that equation, combustion analysis equation, let's try and solve this. The question specifically states that you have, let me write this down. It says that there's a hydrocarbon and we're not sure what that hydrocarbon is. So, but there is a hydrocarbon, so I know that it's burning. I think it's hydrocarbon is burned in excess oxygen, so there's complete combustion happening. So I'm going to bring that hydrocarbon equation that the unknown hydrocarbon. This one was what was it? Let me quickly check. It was x plus y by 4. So I'm just going to write that down. It's going to be x plus y by 4. O2 molecules over here. And on the other side, I have x CO2s and y by 2 H2Os, right? So that's the first part. I know the equation of the hydrocarbon, of the unknown hydrocarbon. Now the question specifically states that the amount of hydrocarbon that's burning is 10 cm cube. So that means this is 10 cm cube. And it's reacting with 70 cm cube of oxygen, which is in excess. So it means that we're not sure what amount of oxygen it's reacting with. But again, we actually know this because if you read the question further, it says that 20 cm cube of unreacted oxygen, like the final gaseous mixture contains 20 cm cube of unreacted oxygen. So that means if you added 70 cm cube in excess and 20 cm cube are left at the end of the reaction, so that means how much oxygen is reacting? That's going to be 50. So this over here is 50 cm cube of oxygen that's reacting. And how much carbon dioxide is produced? It's 30 cm cube. So I have these numbers with me, and he did not tell us that whether he's measuring the volumes at room temperature. So I can't really calculate moles, but you're being told that they're being measured under identical conditions. Now for gas volumes, previously we did questions related to gas volumes. I told you that gases, their moles and their volumes react in the same ratio. So when you're dealing with gases in an equation, the mole ratio and the volume ratio are exactly the same. I said they are exactly, mole and volume ratios are exactly the same. That's for gases. So that means if 10 is reacting with 50 and it's producing 30, that means that according to this ratio, 1 mole, the whole number ratio in terms of moles is going to be 1 mole would react with 5 moles and it would produce 3 moles of carbon dioxide. Okay, remember we did this earlier that for any gas, and I'm going to repeat that if you have two gases reacting, for example, there's hydrogen reacting with oxygen and forming, let's say, water. Now these two are gases. So if you have two gases reacting, and let's say 2 moles reacts with 1 mole, then at RTP, the volume of this would be 48 dm cube. The volume of this oxygen gas is 1 mole, that's 24 dm cube. So the mole ratio and the volume ratio, it's 2:1. This is also 2:1. So whatever volume ratio is, that's going to be the mole ratio as well when you're discussing gases. So using that, I've been able to figure out. Let me rub this off. Now using that, I've been able to figure out that 1 mole reacts with 5 moles to produce 3 moles of carbon dioxide. Now the whole thing is very easy. What did the equation tell me? That there was 1 mole of hydrocarbon, right? So 1 mole. According to the information that's provided, how many O2s should it react with? It should react with 5 moles of O2. So that means the value of x plus y by 4, this number that I'm getting, it is actually 5. Because 1 mole reacts with 5 moles of O2 according to the ratio. So that means this entire thing, this number should have been 5. And 1 mole produces 3 moles of carbon dioxide according to the volume ratio. We figured that out, that 1 mole reacts and produces 3 moles of carbon dioxide. So that means the value of x is going to be equal to 3. And so we figured out the value of x. It should be coming out to be 3. And if I substitute x over here in this equation, it's going to be 3 plus y by 4. And that would be equal to 5. And I can get 3 on the other side. This would become 2. And this 4 would go and multiply with it. So that means y is coming out to be equal to 8. So that means my x is 3 and my y is 8. So this hydrocarbon is actually C3 and H8. So is this question clear? Achha, so this over here has to be 1 mole. So let me convert this into a whole number ratio. So I'm going to divide everything by 0.2. So let's divide this by 0.2. So if I divide everything by 0.2, the mole ratio is going to come out to be that if this is 1 mole, the amount of carbon dioxide over here would be 4 moles. And the amount of water that's going to be produced is also going to be 4 moles. So that means the value of x over here is equal to 4. So we found the value of x. It's coming out to be equal to 4. And the value, this number over here, this y by 2 number would be equal to 4 as well. So if I put that equal to 4, the value of y comes out to be equal to 8. So my x is 4 and my y is 8. So the answer would be C4 and H8. Is this question? Now, this question is, he's actually done the balancing for you. Honey, you're always going to apply the same method. The only thing is the question would sort of be presented in a different way, but the method would be exactly the same. For example, if you look at this question over here, he's saying T is an alcohol, and he's given you the equation, the balance equation, but not in terms of not the way exactly that we balanced it, because there's an O as well. So he's using a different balancing, but we're going to use the same method. He's saying the alcohol, the volume that it occupies is 20 cm cube. So I can write that down. The volume over here that's being occupied is 20 cm cube. That's the first information. And what else is given? It's given that the sample was completely burned in 200 cm cube of oxygen. Actually, now in this question, it's the tricky part is you have to figure out the amount of oxygens, carbon dioxide, and water molecules yourself. So the first part is he's burning it in 200 cm cube of excess oxygen, and the final measured volume under the same conditions as the gaseous sample was 250 cm cube. So the final mixture that you're getting that the final volume of gas is 250 cm cube. And remember, he's using 120 degrees centigrade as the temperature. That means this water over here is not going to be in liquid state, but it would be in gaseous state as well. Usually we consider water to be liquid, but in this case, the temperature that he's using, we have to be careful what temperature he's using. So this is part of this final mixture of gases. So what does it contain? It contains steam, water vapors, that is going to be present in this final mixture. So there is, just one second. So there is water in the form of steam. Then there is carbon dioxide gas that's going to be produced. So that is present. And because he's using an excess of oxygen, so a lot of oxygen would be unreacted. So there's going to be unreacted oxygen that would be present as well. Now that's the final mixture of gases. He then says under these conditions, all water present is vaporized. Removal of the water vapor from the gaseous mixture decreases the volume to 170. So when he gets rid of the water, the volume decreases to 170. Now that indicates that if it decreases 170, that means what is the volume of water that's over here? That's going to be 80 cm cube. Okay, is this part clear to everyone? Okay, so you are 250 cm cube. Immediately when you remove the water, it decreases to 170. That means water is 80 cm cube. I said then the next part is treating the remaining gaseous mixture with concentrated alkali to absorb carbon dioxide decreases the volume to 110 cm cube. So when he gets rid of the carbon dioxide to absorb the carbon dioxide, when he removes all the carbon dioxide, the volume then decreases to 110 cm cube. So that indicates that how much carbon dioxide did we have? 170, it decreases to 110. That means the amount of carbon dioxide in this mixture is 60 cm cube. That's the amount of carbon dioxide that has been produced. And what's this 110 left at the end? That's the unreacted oxygen because you've gotten rid of the water, you've gotten rid of the carbon dioxide. So the only thing that's left in the whole mixture is the unreacted O2. That's the only thing that's left at the end. So shuru mein oxygen, what was the amount of oxygen that was added initially? 200. What's the amount of oxygen that's left at the end? 110 cm cube. That means what's the amount of oxygen that actually took part in the reaction? 200 added, 110 left at the end. So that means there is 90 cm cube of oxygen that is actually taking part in the reaction. So is this clear up till this point? Is this clear to everyone? Okay, just write yes or no. So now, now the next part. Now we can actually solve the question over here. The next part is use the data given to calculate the value of x. Now the data that's given, I need to find the mole ratio. Like 1 mole of the hydrocarbon produces how much carbon dioxide? That would give me the value of x. So if I use the ratio, which is 20 cm cube, 90, 60, and 80, the numbers that I'm going to get are, what are the numbers that I'm going to get? I'm going to get, this would be 1 mole of this would react with, according to 2090 ratio is 1 ratio 4.5. So that means Z is 4.5. And 20 ratio 60 is going to be 1 mole ratio 3 moles. And 20 ratio 80 is 1 mole ratio 4 moles. So that means the value of X is actually 3 moles, right? One molecule, one mole is going to react with 3 moles of CO2, and 1 mole is going to produce 4 moles of H2O, which means Y by 2 over here is going to be equal to 4. So which means Y would come out to be, if I multiply this by 2, Y would come out to be equal to 8. I mean, that's the next part. So we figured out what the formula of the hydrocarbon is, C3H8, and there was an O as well in it. I mean, the equation that he balanced, there was an O in it as well. So we were able to figure out we were able to figure out the formula and the ballast equation. So you have to complete the equation. You have to write the complete combustion equation for the alcohol, and the rest is named the alcohol as well. Okay, so is this clear? I said the 60. Sanjita, you didn't understand why you're getting 60 cm cube, or just 1 second. So I'll just quickly recap the previous question. Just 1 second. So where did we get the 60 cm cube? Remember, if you look at the question over here, when the combustion happened, the final volume measured was 250 cm cube, right? So what did the final volume contain? That's 250 cm cube over here. It contained the water vapor that's produced, it contained the carbon dioxide that's produced, and it contained the unreacted oxygen, because he explicitly stated that the oxygen was in excess. So there would be unreacted oxygen over here as well. And after that, he said that when he removed the water vapors, the 250 cm cube, which is the total volume of the gases that was produced, it decreases to 170 cm cube. So the 250 cm cube changed into 170 once you got rid of the water. So that means the volume of water in the whole gaseous mixture was 80 cm cube. And then it goes on to state that when the remaining gaseous mixture was then treated to absorb the carbon dioxide, the volume decreases from 170 to 110. So when you remove the carbon dioxide, okay, so look over here, when you remove the carbon dioxide, previously the mixture volume was 170, but now it's 110. So removing carbon dioxide removes the volume of carbon dioxide. So what is the difference? I mean, 60 cm cube of carbon dioxide probably got removed. Sanjeeva, is this part clear? So let's try and do the next question. Would be very similar as well. So we're going to try and do that question as well. 1 second. The next question is, now he's given us the balance equation. Remember, this would not always be provided. There would be a lot of questions where this equation is not given. Memorize this equation. Again, it's a very similar question. Look at the temperature now. Now be very careful. At 37, water is not going to be in gaseous state. So remember, in the gaseous mixture, water would not be present because water would be a liquid at 37. So again, he's burning 200 cm cube of oxygen. The final measured volume under the same condition of the gaseous mixture is 150 cm cube. So the final, after the combustion, the final gas volume is 150 cm cube. What does it contain? The gases would not be comprised of water. Water would not be a part of that because it's liquid. And he also explicitly wrote in the question that water produces liquid and its volume can be ignored. What's produced is carbon dioxide. So this is carbon dioxide. And what else? The other thing that's going to be produced is the unreacted oxygen that's present, because he added oxygen in excess. So there would be unreacted oxygen also present in the mixture. So this is 250, this is 150 cm cube. And it then states treating the gas mixture with concentrated alkali to absorb the carbon dioxide decreases the volume to 50. So as soon as you got rid of the carbon dioxide, the volume decreased to 50 cm cube. So that indicates that the carbon dioxide volume was 100 cm cube. Because it was 150 originally, you got rid of the carbon dioxide, the volume decreases to 50. So the volume of carbon dioxide is going to be 100 cm cube, and the volume of unreacted oxygen would be 50. So that means if you added 200 cm cube initially, 50 is still unreacted at the end. So the amount of oxygen that's actually taking part in the reaction is 150, right? Because you added 200 and 50 is still present at the end of the reaction. So that means only 150 are reacting. And what volume of the gaseous hydrocarbon were you burning? You were burning 25 cm cube. So we're now going to do the last part, which is we're going to find the whole number ratio. and we're going to find according to this ratio, if 1 mole of the hydrocarbon burns, so it's 25 ratio 150, so that's how much? It's going to be 1:6. So 1 mole would react with 6 O2 to produce 4 CO2s. So 25 ratio 150 ratio 100 is, so 1 mole would react with 6 O2s. So this value, this number x plus y by 4 is actually equal to 6. And 1 mole produces 4 CO2s, so the value of x is equal to 4. And we can substitute this value over here. If I substitute 4 over here in terms of x, and I get this to the other side, this would become 2, and 4 would go and multiply with 2, so y would come out to be equal to 8. So x is 4 and y is going to come out to be 8. He did this, the whole question was done in parts, taken in different steps, and you had to figure out the molecular formula of P, the hydrocarbon, which we have been able to figure this out. It's going to come out to be C4 and H8. Okay, so is this question clear now? I say, everyone, any questions about this? Okay, we're going to stop doing combustion analysis questions now. You can practice these questions in the worksheet. वो heading के अंदर है, ठीक है? Try and practice these questions. I'll send you video lectures on that, ठीक है? Solving these questions. अच्छा, now moving on. We're going to try and do probably last one, ठीक है? We're not going to do the rest of the most questions. We can practice them later. These things will continue. I said there's one more thing, and that is we're going to try and do some titration questions. And some difficult titration questions. Okay, not the easy ones. Some difficult titration questions. For example, this one. Now, there's certain questions where the question has a lot of steps. Okay, for example, I'm not going to solve the question right now, but I'm going to explain how to solve this question if the question has many steps. So the first thing is we're going to read the question. We're going to try and figure out how to solve this question. And these questions are very important because you get a lot of 10-15 mark questions on such type of questions. So the question is, there's ammonium sulfate, it's a fertilizer, and you're trying to figure out the percentage purity of the sample of ammonium sulfate by reacting a known amount with an excess of NaOH and then titrating the unreacted NaOH with HCl. So what he's doing is, the first thing is he's reacting this, a known amount, with an excess of NaOH. That's what he's doing. He's reacting it with an excess of NaOH. So this NaOH is in excess. So what you're going to get sodium sulfate, the salt, and water and ammonia. Okay, this is an ammonium salt plus base reaction. You can balance this reaction. This would be 2 NH3s, and there would be 2 water molecules as well. The rest, I think, is balanced. Now, this is in excess, which means that there would be leftover, which basically means that there's going to be leftover NaOH at the end of the reaction. And the question then states that the remaining with an excess of NaOH and then titrating the unreacted NaOH with HCl. So what he does is he first reacts this sample with NaOH, and then whatever NaOH that's left, he reacts it with HCl. So the leftover NaOH, this is where he's asking for the equation with HCl. So the leftover NaOH reacts with HCl, and we know the equation. It's going to be NaCl plus H2O. Now the question starts over here that the 5 gram sample of fertilizer, so this is 5 gram, and that's being reacted with 50 cm3 of 2 mole per dm cube NaOH. So remember, this is in excess. So that's not the exact amount that it's reacting with, but you can find the moles. It's 50 into 2 divided by 1000. So if we quickly do that, 50 star 2 divide that by 1000, I get 0.1 moles. So he's reacting this with 0.1 moles of NaOH. But we're going to write excess. That means this is not exactly the amount that it's reacting with. Some of the NaOH would be left behind after the reaction. It then says when all the ammonia had been driven off, when the reaction had been completed, the solution was cooled and the remaining NaOH was titrated. So this leftover NaOH, which you had over here, was then titrated with 1 mole per dm cube of HCl and its volume is 31.2 cm cube. So we can find the moles of HCl that are reacting with that NaOH. So it's 31.2 into 1 divided by 1000. So that is star 1 divided by, that gives me 0.0312 moles. Remember to sketch things like this. If there are too many steps involved in a question and it's a lengthy question, make sure you sketch something that what's happening, what's the sequence of the steps that are taking place. So you have 0.0312 moles of HCl. Now, based on that, you can figure out the moles of the leftover NaOH. That would be also 0.0312 moles according to 1:1. So we've been able to figure out the leftover NaOH. Now, the next part would be that if you have zero point 0.1 moles of NaOH that were initially added in excess, and there are 0.0312 moles still left at the end of the reaction. So, what are the moles that are actually taking part in the reaction over here? The zero point 0.1 initially added, 0.0312 left at the end. So, you're just going to subtract this. That 0.1 were initially added, and how much are left at the end of the reaction? 0.0312 moles. So that gives me 0.0688 moles. So that means the NaOH that's actually taking part in the reaction over here is 0.0688 moles. That's the amount of NaOH that's actually taking part in the reaction. And according to 2:1, I can figure out the moles of ammonium sulfate. I just need to divide these moles by 2. I can figure out the moles of ammonium sulfate over here. So it's going to be 0.0688 divided by, and that gives me 0.0344 moles of ammonium sulfate. Okay, so remember when a question has multiple steps, try and sketch what's going on. Okay, it could be a rough sketch, but always write notes on the question, what's going on, because otherwise it's very hard to actually comprehend the question. So we've been able to figure out the moles of ammonium sulfate finally. And the last part would be, the very last part would be, this 5 gram was impure. So you can't use that mass because it's impure. We don't know what's the actual mass. So based on this, I can multiply it by the MR, which is going to be what? This is 96. 96 plus sulfate is 96 plus NH4 is 18. 18 into 2 is 36. So that's the MR. And if I find that out, it's going to be 96. So 0.0344 would be multiplied by 96 plus 18 into 2 is 36. And that gives me 4.54 grams. So out of this 5 grams, the actual pure ammonium sulfate is 4.54 grams. And we can find percentage purity. What is percentage purity? That's pure over the impure over the total into 100. So we can finally find that value, and that would be the answer. So the whole question is divided into different steps. Now, if you try to follow the steps without actually sketching what's happening, remember always try and sketch what's going on, because otherwise, by just reading these statements, you won't be able to really comprehend the question very well. No matter what the rough sketch is, but if the steps are a lot, try and sketch what's going on. Okay, 5 grams of ammonium sulfate was added to an excess of NaOH. Then there was leftover NaOH. That leftover NaOH was then reacted with HCl, and then NaCl and water were formed. He gave you the moles of HCl. You figured out the moles of NaOH that were left over. He gave you the moles of excess NaOH that were added. and you also figure out the moles of the leftover NaOH, which is why you, by subtracting the two values, you were able to figure out the moles of NaOH that were actually taking part in the reaction. And based on that, using ratios, you were able to figure out the moles of ammonium sulfate. So, just an advice, whenever you're trying to solve questions which have many steps, do some sketching. Okay, so what you can do for homework is, I mean, this entire question has been solved. What you can do for homework is not this one, just one second. I'll give you the page. No, not this one. This one is easy. This one. This is page number 86. So try, and it's on 87 as well, probably. Yes. So try and solve this question on page 86. Uh, and see if you could figure this out. Okay, make sure try and sketch what's going on over here. Okay, make sure you're able to comprehend the steps. Is this clear? Okay, I'll send the screenshot right now. चलिए ठीक है, just sending the screenshot. बल्कि I'll post the workbook again. ठीक है, उस पे page 86. Try and open page 86. It's on my laptop. I can't really take screenshots. ठीक है, चले ठीक है, okay. Take care everyone. Lafis.